In this lecture, I'm going to be talking about another approach for name entity recognition. And instead of just token by token and see if it is which name entity it is, we are going to work on spans. So spans are more natural because sometimes our name entities are nested. So we are going to work on span prediction. So we focus on this paper in 2021 from Carnegie Mellon University. Recent years have been the paradigm shift of name entity recognition systems for sequence labeling to span prediction. So I can say this is the old approach and this is the new paradigm. So despite its preliminary effectiveness, the span prediction models by us has not been fully understood. So although this is a very good paradigm that recently many researchers are working on, but it has its own problems as well that we should discover and get mature. So we first investigate the strengths and weaknesses when the span prediction model is used for name entity recognition compared with sequence labeling framework and how to further improve it, which motivates us to make complementary advantages of systems based on different paradigms. They then reveal the span prediction simultaneously can serve as a system combiner to re-recognize name entities from different system outputs. For example, system 1 says this span is, for example, location. But system 2 says, no, this is another thing. And then we combine these different opinions in order to produce a unified output, which has less bias. So most of the existing NER combiners rely on heavy feature engineering. Instead, this span NER model in this paper, they propose for a system combination trained in an end-to-end fashion. Combining complementaries of different paradigms, most previous work performed NERs solely focused on sequence labeling. It is still an understudied topic how systems from different frameworks help each other. No extra training overhead and flexibility use. Existing ensemble learning algorithms are expensive, which usually need to collect training samples by k-fold cross-validation. Producing it's very expensive. And connecting two separate training processes, previously optimization of the base name entity recognition systems and ensemble learning for combiner are two independent processes. But this work shows that they are unified and they share the same task. So NER is frequently formulated as a sequence labeling problem. So we have a sequence like x1, x2, x3, and we say these are the labels, y1, y2, y3, for example. Beginning of person, intermediate of location, and others. So these are the data sets that typically people use for NER. Of course, these are general domains, not biomedical domains. In the previous lecture, I introduced you data sets for biomedical domain, which are huge. Chemical, protein, genes, diseases, there's lots of data sets. So span prediction for name entity recognition. Although this is not the first work that formulates NER as a span prediction problem, I will explain all of these references because they are very interesting. They contribute by exploring how different design choices influence the performance of the span NER and interpreting complementary strengths between SecLab and span NER with different design choices. The span prediction based framework for NER consists of three major modules. First, token representation layer, then span representation layer, and finally span prediction layer. So we have n tokens. The token representations HI is as follows. And this could be any pre-trained embedding. BERT, BioBERT, anything that you are using. It could be GLOV, or it could be pre-trained model, as I said, like BERT. And of course, they use BioLSTM to get these representations, so it's on top of that. So their embedding is fixed, it is freeze, the weights are freezed, but they train the BioLSTM. So we enumerate all the possible M spans for sentence and then reassign a label for each span S. For example, for sentence London is beautiful, the possible spans start and end are, for example, they make their spans like this, 1, 1, 1, 2, 1, 3, but all possible spans. And the boundary embedding, we say the beginning, start and end of token. We just concatenate the start and end of token. But we additionally use this span length embedding because we additionally try to featureize each span representation. So we also give this ZIL. So here comes here, but we also add this length of span in order to have better features. Because this represents your span, so the better features you have, the better representation of span. Now that you have the span, why not make a dot product and then exponential of that to get the score? So for any span, we have the label. And YK is the learnable representation of the class K. So regarding the flat NER task without nested entities, we present a heuristic decoding method to avoid the prediction of the overlap spans. Specifically for those overlapped spans, we keep the span with the highest prediction probability and drop the others. So span NER as a system combiner, so the basic idea is that span prediction itself can also conceptual as a system combiner to recognize named entities from different systems outputs. So we recognize, and so P is the combined, this one is the combined probability that span S can be assigned as a label L, and the score is defined before. So the final prediction is just over all the labels. So because we have different systems, different models, each one says differently, so we take the max.